Good morning, guys. I hope you're doing well. Let's see. A couple of things just off the top of my head before we get started. A reminder that your lab final is this weekend. It starts on the 21st, ends on the 23rd. It is available all the time during those days, so you will be able to do that. There is some review material for that on D2L, so make sure you've taken a look at that. And if you have any questions, comments, problems, please let me know. The test is 90 minutes enforced. It is going to feel like you need more time than that, and I apologize for that, but that's the departmental final. That's the way it works. So, sorry. That is the lab final. There are some labs that are still due this week. There is some ALEKS homework that will be due on Saturday because the next test is Monday. So that means that the ALEKS homework will be due on Saturday, 2 days before. If you have any questions, comments, problems on that, please let me know. Again, those due dates are put there so that you guys have to work on that material in a timely fashion. But I am not a huge, proponent of killing you with those due dates. So if you need additional time, we can definitely talk about that. As far as what's going to happen this week, we have one more lecture of new material, and that's the one for today. Then we have some review that we can do for exam 2, review that we can do to set up for exam 3, and stuff that we can review to get ready for the final. So today will be the last full lecture. I will be available both today and Friday, Wednesday and Friday, during our normal class periods, and I will be in the WebEx session on Monday during your test, just like always, in case anybody has anything. I think that's all of our, oh, there's one more logistical thing I have to talk about. I am normally here all day on Tuesday, but tomorrow I have a delivery that I have to get at the house. So I'm going to be virtual tomorrow. I will be on campus on Thursday if anybody wants to come and see me physically. So that's a reverse from the way it normally is. But I will still be doing my virtual office hours tomorrow the same way I normally do. So just an FYI for you guys, because that may change things a little bit for anybody who might have wanted to come in and see me. So questions, comments, problems before we get started on anything else? Okay. So the last thing we're going to talk about, we're going to start with our discussion of acids and bases. And for anybody who's planning on taking 111, this is exactly where we're going to pick up. So we will start with our discussion of what are acids, what are bases, how do we define them here? And then in 111, we start doing a lot of math that's involved with that. This class doesn't do that, that class does, so that's how we work that. But these are things that you will need to know for this particular test. All right. So we will talk about acid-base reactions. We'll remind ourselves, what is an acid? What is a base? From the information that we talked about when we talked about aqueous solutions. We talked about acids and base there. So we'll talk about some of the properties that they have, the different definitions that they have, what it means to do a neutralization, and some of the gas formation reactions that go on with that. We'll then start talking about some new topics, acids and bases and their conjugates. We'll talk about the acid-base properties of water, and that will include a discussion of equilibrium and equilibrium expressions. We'll talk about the ion product of water, Kw. We'll then talk about the pH scale, how we define our acids and bases and neutrals on that pH scale, what exactly pH means, how we can calculate pH, and how we can calculate the H3O plus concentration from the pH. We'll then talk about POH, which is a very similar thing. I'll then walk you through the fun box, and then we'll talk about the strengths of acids and bases, and then we'll talk about the acid-base properties of salts. So that's where we're going with that today. All right. A little bit of review from previous, if nobody has any questions. Okay. That's not what I wanted. That's what I wanted. Okay. So from what we talked about previously, I have a soda that's at ground level, and I move that same soda to Mile High Stadium in Denver. Where will the soda have more carbon dioxide in? Well, this is a question about the solubility of that gas, the carbon dioxide in that liquid, okay? We talked about the solubility of gases in liquids, and one of the things that we said about that was that we have higher solubility of that gas in that liquid when there's a higher pressure above that liquid. Higher pressure occurs at ground level than it does at Mile High Stadium. Higher up we are, the less pressure we have. So I would expect that there would be more CO2 in that soda at ground level. Okay. For the following combinations, which of them are considered solutions? Okay, when we talked about solutions, a couple of things were always common, and that was that there were liquids involved. So we have gases that are dissolved in liquid, we have solids that are dissolved in liquids, and then we have liquids that are dissolved in other liquids. So those are the solutions that we talked about. There are solid-solid mixtures, there are gas-gas mixtures, there are solid gas mixtures, but those are not considered solutions, okay? So our definition involves it having a liquid with it, okay? In terms of supersaturated, saturated, and molality, I'm going to do molality first because it's a little, in my head, it's a little easier. Molality is a unit of concentration. And we use these brackets to indicate concentration. And it is defined as the moles of our substance, our solute, over our kilograms of solution. So that's our molality, and that's little m, and we try to italicize it as best we can, but I'm not very good at that. So little m is what we need for that. That's molality. When we talk about supersaturated and saturated, a solution is saturated when it has as much solid as it can have at a particular temperature without that solid precipitating, okay? So it's a very finite space where we have saturation. So I can get no more solid in solution without it precipitating out. All right, so that's saturation. When it's supersaturated, then I have technically more solid in solution than there should be at that given temperature. And if we're careful about how we manage this, we can raise the temperature, get more stuff into solution, let it cool very carefully, and keep that extra stuff in solution. So that's typically how we get a supersaturated solution. So it contains more solid than we would normally expect at that temperature. Okay? So those are our definitions there. Questions, comments, problems on any of that? Okay. So a little bit of review from what we have talked about previously. We talked about properties for acids and bases. We said that acids have a sour taste. They do change the color of plant dyes. They react with some metals to make hydrogen gas. They react with carbonates and bicarbonates to make carbon dioxide, and they do conduct electricity. Our bases are bitter in taste. They feel slippery like soap because soap was made out of lye, which is sodium hydroxide, which is a base. They do change colors of plant dyes, so that's not really helpful to us because an acid and a base both do those things. And their aqueous solutions, base solutions, do conduct electricity. So both acids and bases are electricity conductors. They both react to plant dyes, okay? But their taste are different. I do not recommend tasting them, just an FYI for you guys. But that is something that we can use as a way to figure out what we're talking about. But there are some other ways that we can do this, and that's part of what we'll talk about today. When we talk about definitions for acids and bases, our initial definitions state that acids are donators of H+. Okay? Initially, we defined a base as something that donates OH- to solution. However, that doesn't necessarily cover everything that we know is a base. And so we have to expand that definition to not only generating OH- in solution, but also accepting protons. So if it can accept a proton as opposed to giving one up, then it's a base. Okay. So a couple of definitions that we deal with for those. Now this first definition is called the Arrhenius definition. That's a guy's name, so that he's the one who defined it that way. After that, we have our Bronsted-Lowry definition. So we usually call him Bronsted because it's a bigger thing. You'll sometimes see me do this as BL because it's Bronsted-Lowry. So that's the way that in my head that gets shorthanded. So those are our definitions for acids and bases. So acids donate H+, bases either accept that H+, or they generate OH- in solution. Okay. When I have a neutralization reaction, that is considered a complete reaction of equal moles of acid and base, and that forms a salt and water. When we say salt, we mean something that's ionic that then comes apart in solution. So sodium chloride is a salt, okay? NaCl is something that's formed when we have the acid-base reaction between hydrochloric acid and sodium hydroxide. We then make H2O and NaCl, and that NaCl in solution becomes Na plus, sorry, and Cl minus. So those are the ions that I get from that. So when we say a salt and water, we mean something ionic like this, not necessarily table salt. Now, the number of moles required is dependent on the number of acid/base things present in the molecule. Okay, what do we mean by that? Well, if I look at the reaction that I'm looking at right now, HCl plus NaOH, I know that I need one HCl to react with one NaOH to make water and my sodium chloride. That's not always the case. Okay, sometimes we react with other kinds of acids. One of the other acids that we talk about is H2SO4. Okay, this is sulfuric acid. Notice that the H out in the front looks a little bit different. There's one H on the front of the HCl, but there are two H's at the front of the H2SO4. And so that means we have the ability to donate 2 protons on an H2SO4, which means that it's twice as effective as an acid because there's more protons that I can donate. Okay? So if I was going to react this with NaOH, I would still get H2O as a product. I would get Na2SO4 as my other product, my ionic compound. And of course, since it's an Na plus and an SO4 2 minus, that's why I have Na2SO4. Okay? But this is not yet balanced. Okay? I know that I have 2 NAs on the product side, only 1 on the reactant side, so I need to put a 2 there. And once I do that, I can see that I have 2 hydroxides and 2 protons that come together to make 2 H2O. So one of the things that we start to see when we start to balance these kinds of reactions, we get used to the chemistry that's involved here, is that we're now looking at the donation of this proton being picked up by this OH group to make the water. And so I need to balance and have the same number of H plus as I do OH minus. Okay, so it changes the way that we balance these things a little bit. At least it can. It doesn't have to, but I find it a little bit easier to think about it in that respect. So it's entirely up to you how you handle that. Okay, just make sure that it's balanced. And so that stoichiometry still is really important for what we're doing. And most of the work that we do with acids and bases is 1-to-1 ratio. It's true, but that doesn't mean that that we can or should ignore that ratio. It should still be part of the calculations that we do. And so when you see me setting up calculations for the stoichiometry, that's why I always include that molar ratio as a separate step. Okay. Formation of gases. Carbonates, CO3 2-, and bicarbonates, HCO3-, sulfites, SO3 2-, and sulfides, S2-, react with acids to form salts that decompose to produce gases. So Na2CO3 plus 2 HCl gives me 2 NaCl plus H2CO3. But that H2CO3 is not very stable. If I heat that up, it spontaneously decomposes to become H2O and CO2. So the formation of that gas is very normal under those conditions. All right, all 4 of these compounds will do that and will produce gases out of it. I do not expect you to predict those products. If I were to ask you to balance an equation like this, you would be told I am reacting sodium carbonate with hydrochloric acid to give me sodium chloride, and dihydrogen carbonate is the way that this would be listed. So dihydrogen meaning H2, carbonate CO3. So there is that. Questions about any of our review material. Okay. And when we talk about acids and bases, one of the things that we talk about is that an acid can donate a proton, right? So once it's donated that proton, it's now no longer an acid. It is now a base. Okay. So once I have donated this proton from HCl, I'm left with that Cl minus, right? And so the difference between that acid and that base is one proton. Okay. So my conjugate acids and bases differ by one proton. That's it. We talk about the base NH3 and its conjugate acid. It's picked up a proton because it was a base, so it picked up a proton to become NH4+. HF is an acid. It donates that H plus and becomes F minus, which is its conjugate base. OH minus is a base, so it can pick up a proton to become H2O, which is its conjugate acid. So what I've done here is that all of these things in red are acids, all of these things in blue are bases. Okay. And again, once we have an acid like HCl and we donate its proton to become Cl minus, we talk about that Cl minus as its conjugate base. Okay, so that's the terminology that goes with that. So if we look at this reaction right here for the NH3, this is a base. It accepts a proton from H2O to become NH4+, which is the conjugate acid. H2O here acts as an acid. It donates that proton to NH3 and therefore comes over here after that donation to give me OH minus, which is the conjugate base. Okay. You may be asked, what is the conjugate of this thing? One of the ones I love to ask about is HF and F minus. And that's because HF is a weird acid, so we like to talk about its properties. So HF, F minus, those conjugate acid-base pair. Okay? Questions about our conjugates? Now, I talked about water behaving as an acid in the last thing that we talked about. It reacted with the base, the NH3, and it donated a proton to act as an acid. Water can act as an acid to donate a proton. It can also act as a base to accept a proton. Okay, so it has the ability to do both. All right, the ability to act as both an acid and a base means it is amphoteric. Okay, so the term is amphoteric, meaning it can act as both an acid and base. Okay? So ability to do both. Water can, again, act as an acid and a base. So here we have this H2O donating a proton. This one's blue. This one donating a proton to this other water. All right. This water picks up that proton, comes over here. So this is acting as the base, picks up a proton to become the conjugate acid, the H3O plus. This H2O donates that proton to the other H2O and therefore is left as OH minus. Okay. So this is called the autoionization of water. Auto because it happens between two waters. Ionization because we create ions out of it. And of course, one of the other things that we need to talk about is that when this process actually happens, we end up with this H3O plus. Now, do we always talk about it as H3O plus? No, we don't. So when we talk about the reaction of HCl to give us H plus and Cl minus, technically speaking, this reaction doesn't occur the way that it's been written. Okay, what actually happens is that the HCl binds an H2O, it donates that proton to the H2O and looks like that. Okay. Now, why do we write these two things like they're equivalent? Well, because I know, because I'm a chemist and I've done this for ages, that this species is what actually exists in solution. But that H2O is just a carrier for that proton. Okay. So it's when we write it like this, we're writing a net ionic equation where we're leaving that H2O out. That does not mean that they're two separate species. They're not. they are exactly the same. And that H3O plus is called a hydronium ion. When we talk about H plus and we talk about H3O plus, these refer to the exact same thing. It's just that sometimes we're expressly including the water, sometimes we're not. Again, this is based on that net ionic equation. So since I'm only interested in what the H plus is doing, that's why it's the only thing that I focus on when I do this. Okay, but from a technical standpoint, it always exists as H3O plus and should always be written that way. But we don't always write it that way. It's just one of those things that we do. So make sure that you understand that those things are true. When we talk about a hydronium ion, that's that H3O plus. So this guy is the H3O plus. And when we talk about protons, we're referring to that H plus. Okay. So hopefully that will cover most of what we're talking about there. Questions about that? Okay. In order for us to continue our discussion, we need to talk about another concept, and that is equilibrium. So let's talk for a second about the reaction between A going to B, A plus B going to C plus D. Okay. Notice that each one of these has a stoichiometric coefficient in front of it, so a number out in front that we've multiplied this by, and that is symbolized by the small a for the A. So it's the number that goes with A, and therefore it's the small a versus the capital A, which would be the element for that, even though it's not an actual element. Okay. So A, B, C, and D are our chemical species, the capitals. A, B, C, and D, the lowercase, are the stoichiometric coefficients of each one in the equation. And we have states on each one. This is aqueous, this is liquid, this is solid, and this one's aqueous as well. G is gas. We haven't shown it here, but that is what G stands for, is that gas. Now, when we talk about equilibrium, equilibrium is a condition where it looks like nothing is happening. The reaction in the forward direction and in the reverse direction happen at the exact same time. Right. What the heck does that mean? Well, let's think about that for a second. So we talked about this reaction between H2O and another H2O to give me an H3O plus an OH minus, right? And notice that there are two arrows in this. It's something that I do because I know that this is a reversible reaction. And so I know that the H2Os can react to give me some of this. I know that these can back react to give me those H2Os again. Okay, so I know that it happens in both directions. A lot of the things that we talk about can happen in both directions. Not all of them, but most of them. How do you know whether they do or not? Well, that's complicated and we don't talk about it here. That's something that we talk about in 111, but it's just something that you need to understand does happen, and whether or not it happens is something that we can determine with a lot of math. Okay. But when we talk about equilibrium, we're talking about the rate of this forward reaction being the same as the rate of the reverse reaction. So if I'm standing at 500 feet and looking at this thing, it looks like nothing is changing. Now, if I were to be able to label one of these things, which we can do, we can see that it's still reacting as time goes on. But again, no net change is observed. And so it appears that nothing is happening. Right? That's what we mean by equilibrium. Now, when we have an equilibrium condition and we have a reaction like this one, we can describe that equilibrium with mathematics. Yay, math. Awesome. How do we do that? Well, the way that we do that is with an equilibrium expression. The expression of the equilibrium looks like this, where we have KEQ, K for the equilibrium, is equal to that species, the concentration of it. That's what these brackets are for. So the bracket indicates concentration. Doesn't have to be in molarity, but usually is. So we have our concentration raised to the stoichiometric coefficient. But notice, this doesn't exactly match what I had written on the previous slide. I only have D and A here. Let's go back and look at that reaction for a second and talk about maybe why that might be. So I had this one and I had this one. Those are the only two that appeared. I don't see this one, and I don't see this one. And notice that I underlined the states. There's a reason for that. The reason that we don't see those two species is because the amount of liquid that is present comparative to my aqueous components is huge. And so effectively, I never see a change in that. There's never enough change for me to be able to measure it. So that liquid becomes part of that constant that we talk about. The solid is very similar. Okay, while we can see effects from the solid, it depends on like what its surface area looks like, things like that. While we can see effects there, we typically do not see that that has any effect on anything, and so is not part of that. Okay, no solids, no liquids. Gases and aqueous components both will appear in our KEQs. Okay, so gases and aqueous components. Now, yay, I told you all of this because we have to be able to look at what this looks like for water. This is always temperature dependent. That's the other thing that you need to know, is it's always temperature dependent. Now, what does that look like when we talk about water? Well, remember that we talked about H2O, which is a liquid, plus an H2O, which is a liquid, going to become H3O plus, which is aqueous, plus an OH minus, which is aqueous. And so the only components that will be part of this expression are those two. Those H2O liquids will not be part of it. And so that's how we get this right here. That's where that comes from. Now, that's great. And this is it is a KEQ, but we normally call it KW because it's specific for water. So we normally call this KW. It still has this format. That's fabulous because it gives us a way to calculate the concentration of the H3O plus and the OH minus. And remember that this is temperature dependent. So at room temperature, i.e. 25 degrees, those two concentrations will be equal to each other. Okay, they will be at any temperature, they will be equal to each other, but their values will be different at different temperatures. At 25 degrees, each one of these has a concentration of 1 times 10 to the minus 7th molar. And that means that KW has an expression of 1 times 10 to the minus 14th. Hey, that's awesome. Because what that means is that if I know one of them, I can figure out what the other one is. Okay. Now, that's in pure water. We know that they're equal to each other. Are they always equal? Yeah, not necessarily. Okay. Sometimes that's not the case. Sometimes they're not equal to each other. And so that's where we start talking about, how do I know what this thing looks like, what it is, right? Now, if the H3O plus and the OH minus are equal to each other, then that solution is neutral. Okay, I have the same amount of acid as I do base, so it's neutral. So that's our situation right here. If, on the other hand, the H3O plus is smaller than the OH minus, my H3O plus is low, okay, that solution is basic. If my H3O plus is high compared to my OH minus, that solution is acidic. Okay. Yay, awesome. So if the acid goes up, the base has to go down. So the H3O plus goes up, the OH minus has to go down. Awesome. So those are our conditions for knowing whether it's acidic, basic, or neutral. But here's the thing. This number, big, cumbersome, ugly. Don't like to work with the scientific notation. Can be done, sure, absolutely, but not a huge fan. So when we work with solutions that deal with acids and bases a lot, we don't necessarily deal with them in terms of that scientific notation. We have another way that we can talk about these concentrations. Questions about where we are so far? So like I said, we don't necessarily always want to talk about this in terms of that scientific notation. We can talk about this instead in terms of pH. So that's little p, big H. That little p indicates the negative log, and that H indicates that we took the negative log of the H3O plus. That's what that stands for. So this expression right here is equal to pH. Okay. It gives us a different way to refer to these numbers. Now, because there's a negative in front of it, what we have is that if the H3O plus is a very high concentration, the pH is low. All right, so it's an inverse relationship. So if I have an H3O plus that's greater than my OH minus, my H3O plus is therefore greater than 1 times 10 to the minus 7th, my pH is less than 7. And that's why we get that acids, which is what this is, H3O plus is high, H3O plus is greater than 1 times 10 to the minus 7th, that pH is less than 7, that's an acid. Okay. If my H3O plus is less than my OH minus, i.e. my H3O plus is less than 1 times 10 to the minus 7th, then the pH is greater than 7, and this is basic. Okay. If they happen to be equal to each other at 25 degrees, H3O plus equals 1 times 10 to the minus 7th, and the pH is 7. Okay. Now, these relationships still hold at other temperatures. It's just that we have different values that go with them. So that's something that we will talk about in 111 if you get there. So your pH is going to decrease as your H3O plus increases. So if you have a lower pH, it's a higher concentration of H3O plus. And this is a logarithmic scale. So a small change in pH can actually be a very large change in the amount of acid that is present. Again, we can calculate pH by taking the negative log of the H3O plus. That's this calculation right here. If I need to go the other direction and calculate H3O plus from pH, that H3O plus is equal to 10 to the negative pH. It's the inverse of that, okay, mathematically. Cool, awesome, right. How the heck am I supposed to remember that? Well, that's a good question. But before we get there, let's talk about one more set of definitions. So other things that we can define is a POH. So just like we talked about before, that P means negative log, OH refers to that hydroxide ion concentration. So we take the negative log of the OH minus concentration, and that gives me POH. So it's a logarithmic description of the hydroxide ion concentration. And of course, this gives us the ability to be able to talk about the basic side as well as the acidic side. Now, because I know that at 25 degrees, the value for Kw is 1 times 10 to the minus 14th. If I take that H3O plus times that OH minus equal to 1 times 10 to the minus 14th, and I take the negative log of this entire expression, that gives me pH plus POH is equal to 14. And if you want to see the mathematics on that, it's in your textbook. I'm not going to walk through the whole thing, but that is how we get that relationship, is by taking the negative log of that expression that we had for Kw, this one right here. So pH plus POH is equal to 14 at 25 degrees. Cool, awesome. So if I know pH, I can find POH. If I know POH, I can find pH. Similar to what we talked about previously, if the H3O plus is greater than the OH minus, that means that OH minus is less than 1 times 10 to the minus 7th. So the POH is greater than 7. Right? Because this is the inverse. So if the pH was low, then the POH is going to be high. If we have our H3O plus less than our OH minus is greater than 1 times 10 to the minus 7th, then my POH is going to be less than 7. So higher concentration of OH minus, lower POH. If the H3O plus equals the OH minus equals 1 times 10 to the minus 7th, then the POH equals 7. So POH decreases as the negative log of OH minus increases. Okay. We can calculate POH in exactly the same way that we talked about before. We take the negative log of that OH minus to get POH. And if I need to go in the reverse direction, I can have my OH minus is equal to 10 to the negative POH. Okay, awesome. And I still come back to, how the hell am I supposed to remember all this? Well, here's how we do that. Cool. So what is this thing? Well, we call this the fun box. So it's a pH box. We call it the fun box. This is in your exam handouts. You are going to be expected to use this on your test. So make sure that you understand how to use it. Now, if we're looking at going from H plus to pH, right, we know that we take the negative log. So this shows that pH is equal to the negative log of the H plus. So as I go from H plus to pH, that's the calculation that I do to get from H plus to pH. If I need to go in reverse, and I need to get from pH to H plus, then I take the H plus is equal to the 10 to the negative pH. Okay, so that's that one. Same kind of thing is going to be true on the other side. If I have my OH minus, I can take the negative log of the OH minus, get POH. If I have POH and I need the OH minus, I can have OH minus is equal to 10 to the negative POH. Cool, awesome. That works exactly the same way on both sides. Great. Now, if I know my pH, I can get to POH because my POH is equal to 14 minus pH. I also know that if I have POH and I want pH, I can take pH is equal to 14 minus POH. Cool, that's fun. So those are the three directions that I typically use this, all right? Now, is it possible to work between H plus and OH minus directly? Yes, absolutely it is. I know that the value for the multiplication for H plus times OH minus is equal to 1 times 10 to the minus 14th. And so if I know one of them, I can solve for the other one using this equation. If I want OH minus, that's equal to 1 times 10 to the minus 14th divided by the H plus. So I can use that just as well. But of course, if I know my OH minus, I can take the negative log of that to get the POH. Then I can do the math down here and go back. And once I have the POH, then I can calculate the OH minus using the inverse here. That tends to be the way that I handle it. How you get between these, not important. All right, as long as you're using one of these methods, get between them. That will get you where you need to be. Okay? The only way to make this work for you is to start doing some of these calculations. And you need to be doing them on your own so that you know how your calculator expects those numbers to get put in. So you need to actually do them and compare those numbers to my numbers, the textbook's numbers, the internet's numbers, whatever, so that you can make sure that you've put that in correctly. Okay, and that has a lot to do with the scientific notation and the way that that gets put into your calculator. So make sure that you can get between these values. It is very common for you to get one of these things and be asked for the other three. So in theory, if you've done your practice on these, those should be pretty easy for you to do in theory. So hopefully those are easy points. Okay. So sample calculations. What are we going to see? I have a sample of Listerine. Measure the pH using some pH paper, and I find that it's 4.2. So answer the following. First thing, acidic, basic, or neutral? Well, my pH is less than 7. So this is acidic. That's my reasoning, is because pH is less than 7. If I know that my pH is 4.2 and I want to know my POH is equal to 14 minus that 4.2, which is equal to 9.8, which I actually have written down here. Okay. If I need to know what that H3O plus concentration is, that H3O plus is equal to 10 to the negative pH, 10 to the negative 4.2, which is this number right here. 6.31 times 10 to the minus 5th. And if I want to know what the OH minus is, I can do that using the this relationship here. OH minus is equal to 10 to the negative POH, and that's 10 to the negative 9.8, and that's this number right here. I can also do this with OH minus is equal to 1 times 10 to the minus 14th divided by that 6.31 times 10 to the minus 5th. And no matter which way you do this, you should end up with the same number that we got down there, and 1.58 times 10 to the minus 10th. Okay. So that's what we're looking at there. Now, I want you guys to try to do this on your own. So I have another scenario that's set up here. We want to talk about baking soda, has a pH of 8.3. Answer the questions: acidic, basic, neutral, POH, H3O plus, and OH minus. Okay. I'm actually going to enforce this by giving you a couple minutes to work on this, and then I will come back and talk about what we do, how do we get to that. Okay. But it's important that you do the practice on your own, so try it. See what you think. Okay. I know I didn't give you a ton of time, but I hope that I gave you some time to think about this on your own. This is part of what you will find in the exam 3 prep. So, and that the exam 3 prep is actually really long. It has a number of different typed pages, and you'll find in the exam key that, or in the practice key, that there are worked out solutions in between those questions. So make sure you look at the list of questions to make sure that you got them all, in addition to just looking at the key. So there's a lot of them there. That exam 3 key is not only designed to prepare you for exam 3, but also to cover other topics that we've covered this term that you should be able to answer at this point. Okay. So, has a pH of 8.3. So my pH is greater than 7, so I would call this basic. That's first. If I know what my pH is and I want my POH is equal to 14 minus the pH. That's equal to 14 minus the 8.3, which, no, I can't do that in my head. So I get 5.7. If I want to know what the H3O plus is, then I know that H3O plus is equal to 10 to the negative pH, and that's equal to 10 to the negative 5.7. Sorry, 8.3. Oops, almost did the wrong one. 8.3. And then I do my second 10x negative 8.3. And that gives me 5.01 times 10 to the minus 9th, which makes sense to me. It should be less than 1 times 10 to the minus 7th because I'm above pH 7. If I look at my OH minus, that is also equal to 10 to the negative POH, and that's 10 to the negative 5.7 here. We're supposed to use the 5.7. And so I go second 10x negative 5.7, and it gives me 1.99 times 10 to the minus 6, which makes sense. Again, it's more than 1 times 10 to the minus 7th, because we are basic. I would expect that. Okay. I haven't given a lot of thought to sig figs here. The rules for pH and sig figs are a little complicated, so I'm not going to worry about that as far as sig figs go here. I don't know that there's anything in Alex that's going to be worried about it either, but I will double check that today. So, questions, comments, problems about getting our numbers. So getting to pH, POH, H3O plus, OH minus, given one of those values. And again, all the relationships that I used today, everything that I wrote in here, right in there, comes from that fun box. The only reason that I know what they are is because I have done this 8 billion times. So, questions, comments, problems on that? So the next thing that we need to talk about is the strengths of our acids and bases. Now, in your exam handouts, you'll find a list of strong acids and strong bases. There are 1, 2, 3, 4, 6 strong acids, 6 strong bases listed in that table. Here's the rule that you guys can use for this class. If it's in that list, it's strong. If it's not in that list, it's not. Okay, whether or not you find it in the list of weak acids at the end, if you choose to look at that, doesn't really matter. As long as it's not in the list of strongs, then it's weak. Okay. So the thing with the strongs is that they ionize completely. So when we talked about HCl, we said that HCl becomes H plus Cl minus. Okay. Notice that I've written that as a one-headed arrow. It only goes from HCl to the H plus Cl minus. That's because the H plus and the Cl minus do not come back together to give me back HCl once they've come apart. That does not happen. But there are things that will do that. And one of those examples is HF. So when we write HF, that's always going to look like that. And that's an H plus and F minus. That's what I get as far as ions out of that HF. But that H plus and that F minus can come back together to give me HF back. And that's because it's a weak acid. So it's not completely ionized. All right. HF is a weird acid because it's the only halogenated acid that doesn't completely dissociate. So it's the only one. And the reason that it does that is because it's really, really small. And so it's really hard for it to get those things to come apart. Okay, once they're associated with each other, it's really hard to get them apart. The other thing is there's a lot of hydrogen bonding that goes on with that particular material. And so it's very difficult to break those hydrogen bonds. So that stays together. We have some other things that we can talk about. CH3COOH, which is acetic acid. This is a weak acid as well. Okay. When this dissociates, we end up with CH3COO minus plus H plus. So H comes off. And I took the one off that was by itself. That's what I know, is that I take the one off that's by itself. And was there any particular reason that we write this as CH3COOH as opposed to some other ways that we could write it? There are other ways that I could write it. Yes and no. Part of that has to do with how the structure actually looks. Part of that has to do with the fact that we're emphasizing that it's an acid in doing it this way. Sometimes what you'll see when I try to talk about acids is that I tend to put the H out in front because then you know that it's an acid, that kind of thing. But there's, I mean, as long as we have the same number of things in it. So CH3COOH has 2 carbons, has 4 hydrogens and 2 oxygens. As long as that's what you see, it's the same material. Okay. When we talk about NH4 plus, this is the conjugate acid of the weak base for ammonia, right? So this can dissociate to give me NH3 plus H plus. Sorry. And that dissociation does go in both directions. We end up with NH4 plus and the NH3 together, both of them. So that is weak as well. So NH3 is not a great acid, not a great base. It is a weak base. Okay. So that's one of the things that we look at there. So since these are weak, they're not completely ionized. That means they're either weak or non-electrolytes. Okay. And they exist in equilibrium. But if it's a strong acid or a strong base, such as Na and OH, we get Na plus plus OH minus from that. When we talk about KOH, we end up with K plus plus OH minus. On that one, BaOH2 going to be a 2 plus plus 2 OH minus. And of course, that's completely dissociated as well. Most of our hydroxide bases will be completely dissociated. NH3 is our base that's not a great base, so it can react with H2O to give me NH4 plus plus OH minus, hence why it's a base, because it generates that OH minus in solution. It's also a proton acceptor, therefore it's a base. Okay. So that is what we look at for that. So it's either a strong and therefore completely dissociated, or it's weak and not completely dissociated. Okay, so those are your two conditions that we're looking at there. And one other thing, and I just want to check. Okay, yeah, I want to say here. One other thing that is a result of this is anytime I have a strong acid. So if we talk about HNO3, that's an H plus plus an NO3 minus. If I talk about HClO4, that's an H plus plus ClO4 minus. H2SO4 gives me 2H plus plus SO4 2 minus. And how do I know that it's SO4 2 minus? Because it's in my polyatomic ions list. So I know it's a 2 minus, and therefore I have two H pluses that go with it. This H2 is to make sure that we have neutrality. So they're each H plus, each H is a +1, and therefore I need two of them. So when this comes apart, I get 2 H plus, hence that out there. Okay. All of those dissociations are complete. So I know that they're completely dissociated. What that means, the implication there, is that if I know the concentration of this that I put in solution, say 0.10 molar, then I know the concentration of the ions that I get out of it, right? For every one of these that breaks down, every HCl that breaks down gives me one H plus and one Cl minus. So that means that the H plus and the Cl minus, both of them, are 0.10 molar, because that H plus has completely come apart to give me 0.10 molar H plus and 0.10 molar Cl minus. So if I have a strong acid or a strong base, and I tell you what that concentration is, that represents the concentration of those ions in solution. Okay, so make sure that you remember that complete dissociation means that I know what that concentration is. On a weak, that's not true. If I tell you it's a 0.25 molar HF, I have no idea at this point what that concentration of H plus and F minus is. And that's math that we do in 111. Okay? So we're not going to do the math here. You just need to know that it's not 0.25. Questions, comments, problems on that? Okay. The last thing that we need to talk about, we need to talk about the acid-base properties of salts. Now, a salt is an ionic compound formed by the reaction between an acid and a base. They completely dissociate in water, right? There are salts that produce neutral solutions. There are salts that produce basic solutions, and there are salts that produce acidic solutions. Salts containing alkali metals or alkaline earth metals, neither ion reacts with water to form H plus or OH minus. So if I have an an HCl, right? And that comes apart and gives me an H plus and a Cl minus. And I have an NaOH, and that comes apart and gives me an Na plus and an OH minus. When these come together, I'm going to end up with that H2O from this guy right here and that guy right there. Those two make my H2O. And then I'm left with that Na plus and the Cl minus. But that Na plus and that Cl minus are still aqueous, which they were before, so there's no actual chemistry that goes on there. They're just still present. Neither one of these things, because this is a one-direction reaction, can back react with the water to give me anything else. That does not happen. And that's because this came from a strong acid and a strong base. So the salt from a strong acid, strong base reaction will not have the ability to react with water to give me back anything else. Okay. So that's exciting, awesome. But if I have a solution made from a strong base and a weak acid, so strong base NaOH, weak acid HF, okay, I know that technically this is an Na plus an OH minus plus an H plus an F minus, okay, and of course this H plus and the OH minus make an H2O, and then the Na and the F are still in solution, so that gives me H2O plus Na plus F minus. And that's where things get interesting, because this F minus doesn't necessarily want to stay F minus on its own. Remember that we talked about the fact that F minus can back react with the water to give me back HF. And when it does that, it's because it abstracted a proton from here. So the F minus picks up a proton from H2O and leaves me with OH minus. And so that reaction therefore raises the pH. So that's why we say it produces a basic solution. Okay? It's the reaction of that ion to give me back HF. We can see the same kinds of things when we talk about salts that produce acidic solutions. So we can talk about a strong acid, like HCl, and that can react with a weak base like NH3. And technically what happens when this occurs is that I have an H plus a Cl minus plus the NH3. That gives me an NH4 plus that Cl minus. Okay, so I've taken, this guy has picked up the proton here and leaves us with this Cl minus. Now that NH4 plus, it's not great being this direction, so it can come back this way, but typically it doesn't necessarily come back in that fashion. Okay, it doesn't always just come apart to give me that H plus back. Right? Typically what it does is it'll find another H2O and say, I don't want this proton, you take it, and give me that NH3 back. And so we generate this H3O plus, which then lowers our pH. So depends on what made these things, what kind of chemistry I'm going to see. So if it's made from a strong acid, strong base, then I don't have to worry about it. If it's made from a strong base and a weak acid, I have to worry about it. That's going to be a basic solution. If it's made from a strong acid and a weak base, then I have to worry about that. That's going to be an acidic solution. And this is why. Now, what happens if the acid and the base are both weak? Interesting question. Because, I mean, that's the next logical question for me. We talked about what happens with strong acid, strong base, strong acid, weak base, strong base, weak acid. Well, what happens if they're both weak? Interesting. It's complicated, is really the answer that we come up with. And since we don't talk about the math here, there's no way for us to be able to look at that and say, oh, it's going to do this. Okay. It is something that we can do if we're looking at the equilibrium constants, but we haven't talked about the values for the equilibrium constants. So we're not going to cover that here. As far as weak acid, weak base, that is not something you should be asked to predict. All right. As far as some other things that we may or may not see, we have some anions that can act as both acids and bases. So one example is HCO3 minus. So this is an anion. Notice that it has this H out in front, so it can donate that. It can react with an H2O to give me an H3O plus that CO3 2 minus. So we've moved that proton off of that and stuck it on here. Okay, so that's one thing that we can do. The other thing that it can do is that HCO3 minus, instead of donating a proton, can take a proton. And when it does that, it becomes H2CO3, and we're left with an OH minus. Okay? So it is possible for it to both accept a proton or donate a proton, therefore making it amphoteric. Again, amphoteric. Capable of being both an acid and base. Okay? So again, do you need to know that it can do this? Yes, absolutely you do. This is something that you may see on the final. You may see, hey, what's the conjugate of this? And it may not tell you if it's a conjugate acid or a conjugate base. And so you need to know that you can either donate a proton to make it an acid and therefore get the conjugate base, or you can pick up a proton and therefore it's acting as a base and therefore you get the conjugate acid. Okay, so both of those are things that it can do. So questions about that? All right, things that you may see, things that we have talked about today. HCl is a strong acid. 0.01 molar HCl gives what concentration of H plus and Cl minus? Well, HCl is a strong acid. If it's a strong acid, which they just told me that it was, then I know that I get H plus and Cl minus out of that. Whatever this concentration is, that HCl, that's what I should get as my concentration for H plus and Cl minus. So H plus is going to equal the concentration of Cl minus. It's going to equal 0.01 molar. And again, that's because it's strong. NaOH is a strong base. 0.005 molar NaOH gives what concentration of OH minus and Na plus? Okay. Strong base. So that means my NaOH is going to give me an Na plus an OH minus. Those two concentrations need to be equal to each other because they both came from the same place. So the Na plus equals the OH minus, which is equal to 0.005 molar. Okay. What is the pH, pOH, H plus, and OH minus concentrations of each solution above? Right. Okay. So let's talk about this one first. Here, I know what that H plus concentration because I know that from the initial setup that I had. So that's 0.01 molar. If that's the case, I can take the negative log of the 0.01 molar, and that gives me pH negative log of the 0.01, and that's 2. My pOH is going to be 14 minus the pH. 14 minus 2 equals 12. And my OH minus is equal to 10 to the negative pOH, which is 10 to the negative 12. And of course, second 10x negative 12 gives me 1 times 10 minus 12. Yay, awesome. Okay, so there's that one. Now, I want to do the same thing with my NaOH that we talked about. Okay, with my NaOH solution, we have the concentration of the OH minus is equal to the 0.005 molar. If I want to find the pOH, that's equal to the negative log of that 0.005. So I can take the negative log of the 0.005, and that gives me 2.30. So that's my pOH. If I want my pH, that's equal to 14 minus the pH, and that's 14 minus 2.30. And that gives me 11.7. for my pH. And of course, my H plus concentration, 10 to the negative pH equals 10 to the negative 11.7. Second, 10x negative 11.7. And that gives me 1.99 times 10 to the minus 12. Okay. So yay, that was fun. Next question. I dissolve NH4Cl in water. Would I expect the pH to be above, at, or below 7? Okay. So I know that NH4Cl has been dissolved in water. I also know that this is an ionic compound. NH4 plus is my cation, Cl minus is my anion. So NH4 plus Cl is going to come apart to give me an NH4 plus Cl minus. The NH4 plus I know can react with water. And it does so in this way by donating the extra proton that it has. So I get an H3O plus out of that, and I get NH3 back. Because I generate that NH3, that means that it should be acidic. So pH should be less than 7. Okay? So again, in my head, this always becomes, I have this thing, when it comes apart, what do I get? Once I know what it comes apart to be, will either of those react with water to give me something that will change the pH? And of course, if I were to do the Cl minus, that doesn't react with H2O to give me back HCl. So that's not a reaction I'm going to see. Okay. I dissolve NaCH3COO in water when I expect the pH to be above, at, or below 7. Okay, so I'm going to approach this in exactly the same way. I know that this is ionic. I have an Na plus. And then the rest of this, that CH3COO minus. Now I look at this CH3COO minus and I go, wait, okay, I think that that's related to a weak acid, which it is. It's the conjugate base of a weak acid. So I know that that CH3COO minus plus the H2O will give me back that weak acid, that CH3COOH plus OH minus. And the formation of that OH minus means that my pH will be above 7. Okay. Conjugate acid of HI. All right, if I want my conjugate acid of this thing, then I have to add an H plus to it. If I want to take that base and make it an acid, I need to add an H plus. So I have my I minus, I add an H plus to that, and it gives me an HI. All right, and I'm going to write that like this. It's just indicating what that would look like. So that gives me an HI. That's the conjugate acid of that particular species. Okay. What's the conjugate base of NH4 plus? Well, NH4 plus can act as an acid by donating a proton. So when it donates that proton, I get H3O plus NH3 after the loss of the proton. So this is the conjugate base that I'm looking for. Okay. So in every case, it's only going to be different by one proton. I do not need to write the entire reaction. The only reason I do that is to make it clear that that's where it came from. But the difference between these two is one proton. And the difference between these two, right there, is one proton. Okay. One of them I added because I'm looking for the conjugate acid. One of them I subtracted because I'm looking for the conjugate base. Okay? So learning definitions, practicing what's the conjugate of this, that, the other, predicting pH based on the species that you have, knowing what those concentrations are based on what you put in there, you know, strongs we know, weaks we don't, that kind of thing. Identifying what are strong acids, what are strong bases, what are not. Those are things that you should be practicing, and then working with that the fun box to find pH, POH, H plus, and OH minus. And you can do that for any value you want. Just pick one and find the other things that go with it. And if you pick a random value and you don't know what the other ones are, then ask me, and I would be happy to work through that with you. Okay. So those are things that I would expect based on what we've talked about today. Do we have any questions, comments, or problems about what we talked about today? Well, that brings us to the end of our material for the course. Go awesome. I did not talk about exam 2 last time. So for anybody who wants to hang out and talk about the exam 2 and the key that's available for that, that's fine. We can do that. Again, my plan today is to answer any questions anybody has about this exam 2. Next time we can get ready to talk about exam 3. Well, any questions that you have related to the exam 3 practice, which is long. If you have them on Wednesday or Friday, either one is fine. We can spend both days talking about exam 3. We have a day after exam 3 to talk about the final before we take the final. So that's what I got for you guys. I know you have work to do, so feel free to go do it. If you got questions, I'm here.
Hey, Professor, can you hear me?
Yes, I can.
So I wanted to say in regards to that one email that I sent you about the about lab 7, I want to say.
Yes.
We figured it out. But I actually had to get some external assistance. So it turns out the significant figures were just being wonky again. There was one because for some sections there was only 2 significant figures, but then in the same box, it was wanting things with 5 significant figures and 3 significant figures, and it was just weird.
Okay. It happens.
It does happen. But what did confuse me, not really confuse me, but kind of concerned me, was when I went to do the post lab and tried to apply the same math that got me the answers in the lab. Whenever I turned it in and looked at the report, my issue, what caused the answers to be wrong, wasn't a mix-up of what the significant figures were, but that the answers themselves were the correct answers were different from the answers that I had gotten.
Do you have examples you can, or well, I can look at what you turned in and I can see. So
yeah, let me pull it up real quick, and I can get that to you. Okay, here we go. Chemistry. Content. Like that. Trying to get to the assignment list here real quick.
yes.
Yeah, here we are. Post lab ideal gas law constant. Oh, it's gonna just make me redo it.
Well, you do have a second. You can do it twice.
Okay.
I can take a look at what you've turned in. I won't be able to do it right this second, but
no, that's fine. That's fine. I'm not exactly trying to shore up your time.
no, that's not what I mean. I just mean it's gonna be a
Oh
minute
no,
before I can.
sorry, I wasn't meaning that. I was more meaning because I know there's someone else here who wanted to say something, so I'll mute myself for a second.
Hey Ash, what's up?
Hey, same thing as him. Like my labs are off right now. Like I did them but like the significant digits and stuff like are off, and some of the questions like I don't even understand, like what they're asking.
Okay,
Um, I was gonna email you about like some of the problems,
sure,
but
absolutely. Or we can talk about it in person. Either one is fine.
are you available today? I can
Yes,
come in.
I'm here today.
Okay, okay, thank you. I'll be
Yes.
there then. Okay,
Okay. All right. We'll chat about that then.
yep, thanks.
You're welcome.
Because I know you have to get out to do the recording, to upload the recording. Also, I'm more apologizing to myself. I overslept by about an hour, so I popped
Oh,
in at 8:59. So I
that's
came
pretty
in
good.
right as you started the sample questions, and I wanted to ask questions because I think I understood a little bit,
Okay.
but I was like, oh my gosh, son of a gun. Um, but if you wouldn't mind, could we actually pull up those examples just real quick?
Yeah. 2 seconds. Let me that one.
So I want to see if I'm working off a hot air or if I actually kind of understood something.
Okay.
So I'll go ahead and say I don't understand the math you did for the third one, where you did like the log 0.01, stuff like that.
Which part of that is unclear? How I got those equations or the actual math part?
Um, so I want to say both
Okay.
because I don't understand log function.
Well, logs are a little bit different. So the equations themselves come from the fun box. And let me show you the fun box. So this is the fun box. This is on the exam handouts.
Oh, I've seen that before.
Right. And this walks you through. So if you have H plus, you take the negative log of that value to get to pH. And if you have pH, you take the inverse, so 10 to the negative pH to get H plus. So that's how you walk through this. Okay. If I have pH, I can get to POH because I can take POH is equal to 14 minus pH. And then if I want to go the other direction, pH is equal to 14 minus POH. Okay. So these guys, both of these are logs and anti-logs. This one is a subtraction, and this one is a division, depending on whether you're working with the p values or not. As far as the logs go, it's actually using your negative key. So whatever your value is, and I'll go back to this one. Where am I? There we go. So if we look at this one right here, and I have my H plus is 0.01 molar. So I would actually hit that negative key under the answer right there. And then I would hit the log, and then I would put in that number, the 0.01, and then hit enter, and I get 2. And then if I wanted to go for POH, this one right here, that's 14 minus that value. So obviously I can do subtraction. So there we go. We got 12. At least my calculator can. I can't. My OH minus is going to be 10 to the negative POH. So that's 10 to the negative 12 because I got 12 when I calculated POH. And as long as it's, a 0.1 kind of like this one, we don't have to do anything with this. This is fine. When we come over here and we have the values that are not exactly, 10 to the negative, whole number kind of deal. So 10 to the negative 11.7, that's going to give me a weird number, which is 1.99 times 10 to the minus 12. So, and again, when I do that one on my calculator, I hit the second, and then it's the same log key. Because when you do the second, it's the inverse.
Yeah.
And then, so you hit the log key, that gives you the 10 and the little superscript on that. And then you hit the negative key, and then you put in your pH, so the 11.7, and that's how I get that 1.99 times 10 to the minus 12.
And that's 1.99 times 10 to the negative 12?
Yeah.
Okay.
Yeah. As I mentioned, I didn't worry about sig figs there because sig figs on pH is complicated, so I'm not worrying about it.
So then we go from the... Because I understand how we're getting on the left side. Then we have the COH plus grams, I think is what that is.
Where?
I'm not sure. COH something might be a J?
Are we talking about this?
No. On the where you're doing the mathematics, on the right side at the top.
So this is an OH minus. That's equal to 0.
Oh, it's just in parentheses. Okay.
Yes, that's a concentration is what those brackets mean.
Oh, brackets.
Yes. And that indicates concentration. We usually mean molarity, but it doesn't always.
Gotcha. So we have that, and then we are going from OH minus to POH, which gives us no, or is that what we're doing right there? OH minus to POH.
Well, here, yeah, OH minus to POH. So I have POH the negative log of this number, which gives me that 2.30. Yep.
Yep, that matches up, and then we get the pH from the POH, and then the H plus from the pH. Got it.
Correct. Yes. That's exactly right.
And then that's just so long as we have just that one number, we can just plug it in through the cycle of the fun
Yeah.
box, and it'll be
Pretty
good.
much.
Gotcha. Okay, awesome. Thank you. And then for the ion anion things, I was noticing that whenever you were doing it, it was, at least in these examples, I'm not sure if this is kind of a constant, but it was always either the transfer of an H or the separation of a nitrogen is what it looked like. So like just what I mean by that. No, I messed that up. A transfer of a is Na sodium?
Na is sodium, yeah.
Okay, because just as an example for the third from the bottom,
Yes.
you I think that's I always get my greater than and less than symbols mixed up. I think you said greater than 7.
Yes, that is correct.
So the Na gets detached from the CH3COO,
Yes, correct.
and then you know that it can interact with H2O to become CH3COOH plus HO negative.
Yeah, plus hydroxide, correct.
Okay. And then so that would be greater than 7.
Correct.
So is that kind of if there is an Na, or I guess could you kind of explain that one to me? Because
Okay.
I want to make sure I get it right.
In both of these cases, so this one and this one, we are looking at what is this species that's in solution. So in the first case, I have my NH4Cl, right? I know that NH4Cl is ionic. It's an NH4 plus and a Cl minus. So that's what I have right here is this NH4Cl comes apart to be NH4 plus the Cl minus. And then I look at those two things and I say, okay, can either one of those react with water to give me something else? Cl minus, if I add an H to that, is HCl. That's a strong acid. That's not going to happen. Okay. But the NH4 plus, if I take a proton off of that, that gives me NH3. And H3 is a weak base, so that will happen. And that's the reaction that you're seeing right here is an NH4 plus the H2O to give me the H3O plus the NH3. Because that reaction does occur. And because of the formation of the H3O plus, my pH is less than 7.
Got you. So because it's forming a base, it'll be less than 7.
No, it's forming the acid.
Okay. Never mind. Sorry.
That's all right. We're making the conjugate base of this thing by creating the H3O plus, which is the acid.
Okay, so we're making it. This is probably a silly question, but how does that work out? Like, why do we do it that way?
What do you mean? Why do we do it that way? I mean, I just want to make sure I'm answering the question you're asking.
Right, right. Because, like I said, I know it probably sounds a bit silly on the surface. So
No,
we're
I just
making
want
the
to make sure.
conjugate base
Correct.
to determine if it's an acid?
I have an acid right here. NH4 plus is an acid.
Okay.
And I know that because it has an H plus that it can donate. And I know
Gotcha.
that because it has H on it and it's a positive charge, so it has an H plus it can donate. So that's how I know that.
Gotcha.
So since it has this, I need to know what does it look like when that comes apart. That H plus then goes to the water, because that's what always happens. And that gives me that H3O plus. And then I need to know what's left from that. And that's NH3. That NH3 I know is a weak base, so I know that that reaction can happen. Because that's what I'm looking at. If this one, this Cl minus, were to pick up an H plus, that would be HCl. But this
And that's
reaction
hydrochloric acid.
does not occur because it doesn't go backwards. We don't get HCl back once we've made H plus and Cl minus. It never happens because it's a strong acid.
Gotcha.
So that's what I'm looking at, is what do I get out of that? Is it a strong acid, weak acid? What am I getting? And if it's strong, then I know it's not going to happen. If it's not strong, it's probably going to happen. And therefore, we can talk about what happens when that occurs. So that's that first one. When we talk about the second one, I know that this is ionic as well, because I get an Na plus and then this CH3COO minus. This is an acetate ion. And so those come apart. That gives me this Na plus the CH3COO minus. I again think about, all right, what's going to happen if that Na reacts with the H2O? All right. And if it were to do that, it would not be the thing that picks up the proton. This would be the one that picks up the proton. So it would react with the OH minus, which means that I would end up with an Na plus an OH minus to give me an NaOH. And I know that's not going to happen because NaOH is a strong base.
Gotcha. So it has to react with CH3COO.
Well, it doesn't have to react with anything. The question becomes,
okay.
Can it? And of course, if I look at this one, the answer is yes, because if this reacts with H2O, which is what I'm showing right here, that CH3COOH, I react that with the H2O, that gives me that CH3COOH here, plus the OH minus, and this is a weak acid, so I know that this will happen. Because it makes a weak acid. This one makes a weak base, this one makes a weak acid.
So why wouldn't it work? Okay, so I'm just trying to wrap my noggin around this.
You're fine.
If we're trying to, so if it's not that it will react, but that it can react, we only know what to make it react to if it makes a weak base or acid?
Well,
Or
the question becomes, can this ion react with water? And the answer always is yes, it can. What the question becomes, what does it make when it does that? So that's why I keep saying, okay, if this were to react with the water, I would end up with NaOH. And that's not going to happen because that NaOH that I would produce is a strong base. So that's not going to go that direction. It only goes the other direction. I only get Na plus and OH minus out of that. I don't ever get that NaOH back.
So it'll never revert. So, okay, if I'm understanding this correctly, once we've done that, once the base of the acid has done that, you can't go back to the base or acid by adding water.
As long as it's a strong acid or a strong base, that is correct.
Right. Sorry. Yeah, a strong acid or a strong base.
Correct.
And then we have the strong bases and strong acids on the handout.
Correct.
So we just determine if it will become one of those
Yeah. And if it
Okay.
doesn't, then the
ish.
question becomes, okay, does this thing that it creates here, this is a weak base. I know that's a weak base because it's listed as a weak base in the exam handouts. It's on the last page. This one also is a weak acid. And I know it's a weak acid because one, it's not in the strong acids. And two, I know that it's in the list of weak acids on the last page. So I try to give you guys ones that are going to be in that list of weeks, just because then you can confirm that that is a weak and it's therefore going to do what what we're talking
Oh yeah, here we go. Weak acids, weak bases. Do we need to worry about diprotic and polyprotic acids?
about. No, you do not need to worry. I mean, we talked about it. We talked about the fact that diprotic and polyprotic means that they have more than one proton to give. But the numbers that are there are not for you guys. That's we don't talk about the numbers part of it. Just the fact that they have
Gotcha.
more than one proton.
Gotcha. Then and so our conjugate base is just acquired by what would happen if an acid interacts. I'm taking it NH4 as an acid.
Yes.
If an acid interacts with water, that's what gives us the conjugate base.
Our conjugates are always different from whatever species we're talking about by a proton. So if I'm looking for a conjugate acid, I'm adding H plus to it. If I'm looking for a conjugate base, I'm subtracting H plus from it. Because all of my conjugates are either after I've donated that proton or after I've accepted that proton.
So it's all in the H.
Yes, it's all on the H. I mean, when I talked about that, where is it? So when we talk about our conjugates, we start here with our base, which is NH3, and it picks up a proton from the acid. So the acid donates the proton. When it does that, we end up with this NH4 plus. This is listed as the conjugate acid of that base. And notice the only difference between those two is an H plus.
Yeah.
Here we have our acid, which is donated to that H plus to give me that conjugate base, which is OH minus.
Gotcha.
There are other conjugates and definitions that exist, but this is the only one we're dealing with.
So, okay. So, were the samples covering the majority of things that we covered today?
The majority of them, yes.
Okay.
I mean, it's not everything, but yeah.
Okay. So, I guess what I'll do is I'll go back over the lecture and give you an email if there's anything that confuses me.
Okay, and that's fine.
Then I had one more question.
Yes.
So for the stuff that's due tomorrow night, standardization of sodium hydroxide and post-lab titrations, is that the lab and post-lab? Is that the match? Are those a match for each other?
Yes, except there are two labs. So there's the standardization of NaOH, and then there is the
Concentration of vinegar.
Yes, correct.
Oh, okay. I was reading that as under 420. Yeah, no, that's what was going on. I was literally reading the final submission date as the due date. So I was like, oh, everything's due on the 28th. Okay, I can parse this out by like 2 or so days from each other. And it's like, no, I could not. So, yeah, fun times.
And I apologize for that, but that is in the schedule that's on D2L as well.
Yeah, no, that's also part of the reason why I was more saying, as much as I would like one, I don't feel it's really appropriate to ask for an extension.
No, see, but that's the thing. it's not your fault that you misread something. If it was that big of, I mean, this is one of those things where if you were in a job and you had a due date, we would discuss that, one-on-one. You guys are expected to interpret what I've written down, and if you don't ask questions, then I don't necessarily know if you have questions about them. So,
Yeah.
just because I've walked through it doesn't mean you actually understood it. So that is not something I'm going to let hold you up. So those due dates will get changed. I just haven't had a chance to do it yet.
Okay. All right. Thank you, Professor. I really appreciate it. You have been incredibly lenient with me.
Well, I
And
appreciate that. Thank you.
If I could like give you a gold bar, I would, but but I really appreciate it, Professor. You have a lovely day.
Thanks. You too.